particularly interested in the intersection between the Bayesian brain hypothesis and energy-efficient learning. This piece of work is directed in that vein. We're going to be focusing on the synapse, inference of the synaptic weight, the postsynaptic potential amplitude. There exists variation in the PSP. This variation can be explained by several theories. One, that it's simply an artifact of the system, potentially erroneous. Another is that this variation closely resembles the uncertainty of the parameter within the model. This is the Bayesian interpretation. One positive is that uncertainty can be communicated downstream by sampling from this distribution. A downside is that variance from the mean is potentially detrimental to the model, as it can tip the system away from learned optima. In this paper, we'll be talking in terms of a discriminative model, an input, sensory information, and output classification. Another benefit of Bayesian learning is that errors on the objective are weighted by the variance of observations, used for causal inference of model parameters, the synaptic weights. The brain receives information incrementally. Different time points will have different degrees of variance of observations. Time points with high uncertainty on observations should change the model to a less degree. Furthermore, encoding of model uncertainty across all the different parameters allows adaptive learning rates. This means that uncertain weights should be changed more readily by incoming information. This Bayesian learning is why learning optimizers such as Adam learn so fast. Therefore, a normative argument would make the claim that the brain should learn using Bayesian plasticity. However, evolution doesn't necessarily demand criticality of function. We consider energy sparsity to be a perennial selective pressure of evolution. Thus, a learning model for the brain should be energy efficient. We temporarily then put Bayesian plasticity aside, as we now observe what emerges from an energy-efficient treatment of synaptic plasticity. We know that postsynaptic potentials follow a Gaussian distribution when there's multiple physical release sites. We know statistically that the precision of a sampling distribution scales with the number in the sample. Thus, we make the claim that precise synaptic transmission scales with the number of physical release sites. But this is also more energy costly. So our biological reliability cost is inspired by this proportional relationship with precision and n. This reliability cost can be made more versatile, fitting more actual biological relationships of putative reliability cost by bringing in these hyperparameters p and s. They can be loaded with biological meaning. S can represent the scale of the energy cost of recruiting a particular vesicle and active zone. P, the polynomial relationship of recruiting n vesicles, active zones. So fitting this reliability cost to a Quantal model, where n is the number of vesicles, p is the probability of vesicle release, alpha is the Quantal size, we can get the mean of the PSP and the variance of the PSP. Substituting the alphas, we can get this inverse relationship on the top right between n and the variance. Recall that our reliability cost, CBI, was proportional to n and the precision. So we then introduced our hyperparameters p and s, and therefore if we set s equal to that expression on the bottom, we can get our reliability cost in terms of the mean and the variance, the parameters of the Gaussian parameters of the synapse, probability of release, and this energy cost of vesicle release. And the energy cost of vesicle release was estimated by Atwell and Love in 2001, and therefore we get this plot with different coefficients of variation, different amounts of ATP cost, and different vesicle counts in order to achieve different levels of precision. So as precision increases, we need more vesicles, and the ATP cost increases exponentially. So in order to observe energy efficient learning, we need to have our reliability cost to a performance objective, ordinary least squares, in a simple linear model. This admits stochastic distributions for each weight. The scatter plot on the left, along the x-axis we have the weight variance as obtained by this objective. We see that weights with higher variance are more robust to perturbations. This tells us that high variance weights can emit more noise than low variance weights. This alludes to a Bayesian interpretation because weights with high precision from Bayesian inference have a higher likelihood, given the data, more important to the model. And the plot on the right shows that if we add noise to weights proportionally to the variance obtained by the objective, we have a tenfold increase in model robustness as compared to adding the noise uniformly to each weight. The emergence of learning analogous to Bayesian inference can be shown more explicitly in the following. Variational inference is a method of approximating Bayesian inference. This is achieved by maximizing the elbow, the evidence lower bound. Entropy is a term of elbow. The negative entropy is minimized in variational inference. Our reliability cost is an upper bound on the negative entropy. Therefore, optimizing our energy efficient objective approaches Bayesian inference. Learning models best suited to biological agents are filter algorithms due to their use in online learning paradigms. Filter algorithms obtain the best estimate of state if given an objective on all time points previously observed. They aim for the direction of greatest descent in the objective. This is achieved using second-order curvature information. The Kalman filter, the best estimate of state in the least squared error sense, can be derived using Newton's second-order optimization. The Kalman filter can also be derived using recursive Bayesian estimation. We see from our learning rule that the synaptic parameters can be updated using only gradient information. And furthermore, that this learning rule is local to synapses and invariant to the objective of the task. We combine reliability cost with the extended Kalman filter objective. We test performance on a neural network classification task across a range of settings of scale for the reliability cost. As the scale of the reliability cost increases, the effect of the reliability cost on the objective also increases, and therefore precise transmission becomes more expensive. So we get more noisy synapses, and clearly there's only so much noise that the model can take before performance decreases. We see something similar on the bottom row of plots. As S increases, the normalized variance decreases. Normalized variance is a proxy for learning rate, so we see less learning when we have less reliable transmission. This makes sense because less reliable output means less reliable feedback. We've assessed the trade-off between energy efficient learning and performance. Hyperparameter S, the scale of the reliability cost, determined where on this continuum learning proceeded. Both sides of the trade-off have a Bayesian interpretation. The energy efficient objective approached Bayesian inference, and the optimal Kalman filter has a recursive Bayesian update rule. Therefore, given the biological imperative for energy efficient design, there is a high likelihood for Bayesian plasticity.